Hello friends, so till now we have discussed about nucleation in growth during phase transformation, and we also discussed now that how we can find out the time required for transformation. Okay, so we used two ways to do that. One is through TTT curve and another through CCT curves. Now we will go to the actual heat treatments which are used in industry. Okay, so we will try to understand different types of heat treatment which are. So you should know the name and what temperatures they do those heat treatment at. Okay, so this is more like just lot of information, technological information, important for engineer, practicing engineer. Okay. So today's lecture will be on heat treatment. This is a overall one snapshot of heat treatment. Okay, I took it from this particular e-book, a very good book. You can also refer this e-book from Anand Subramaniam in IIT Kanpur. Okay, so heat treatment can be divided into bulk heat treatment or surface heat treatments. In bulk heat treatment, you can have annealing, normalizing, hardening and tempering, Mar tempering, Aus tempering, all these heat treatment we will see. In annealing also it can be full annealing, recrystallization annealing, stress relieving annealing or spheroidization annealing. Okay. And for surface treatment you can have thermal surface treatment or thermochemical. In thermal, okay, it is only the flame, through flame you do take flame and do treatment. Okay. And because as you can see now from after understanding the TTT and CCT curves, suppose I heat the surface by any means which is able to heat only the surface, let us say maybe up to 1 mm or 2 mm depth. Okay, suppose you have induction heating or laser heating or electron beam heating where they have very concentrated source and the heating will be very localized, and then you stop the heating. What will happen? The whole bulk of the material is still not heated up, it is still maybe at room temperature or let us say slightly higher temperature. Okay. But the surface is went into, let us say, in the austenite phase by heating. So now the surface get so much material which is not heated up. Okay, and so it will cool very rapidly. So you can have localized transformation. Okay, where you can get a different type of phase, let us say Martensite phase. Okay, and Martensite phase is a very hard phase. Okay, it has a very high hardness. Okay, so by doing this type of thermal treatment, I can have a very hard surface. Okay, and still my bulk of the material is soft. Thermochemical, if you see, okay, already we have discussed about diffusion. So you can have carburizing where carbon you can diffuse, and you can understand that by changing the chemistry I can change lot of things. I can change the microstructure locally. Okay, I will have more of perlite. So maybe better properties, better mechanical properties on the surface. You can do nitriding similar to carburizing where now nitrogen is diffused inside the surface, or you can have carbonitriding. Okay. So there is a plethora of heat treatment processes. Okay. Right now we are concentrating on the bulk heat treatment. Before going further, let us see that what are the temperatures which are important in the iron carbon phase diagram. Okay. And we are only concentrating in mostly the part where the steel is going to be there. Okay. And also only in the part where you are going to have a solid state phase transformation. So you have austenite here. Okay. Okay, I have austenite here. Okay, and you have alpha ferrite here. Okay, and on the other side you will be having cementite. Okay, and this is where you will have eutectoid reaction. So there are two three critical temperatures shown here. Okay, one is this A3 line. Okay, where my alpha plus gamma transform to gamma. You have ACM line where your gamma plus AP3C transform to gamma. okay, and you have A1 line which is related to eutectoid temperature. So, there are couple of important critical temperatures here, okay, and you can see as the composition of my alloy is going to change, the temperature, this A3 temperature is going to change, that is obvious. So, these are critical temperature. A1 is the isotherm at eutectoid temperature, okay. A3 is your phase boundary between the austenite and two phase austenite plus ferrite. ACM is the phase boundary between austenite and two phase austenite plus cementite, okay. So, basically on this we have now also plotted that at what temperatures you are going to do a particular operation. For example, where you are going to do annealing, where you are going to do normalizing, okay. If I want to do normalizing, I will have to go to a temperature above A3. Similarly, for annealing, okay, this is for hypereutectoid steel, normalizing will be above ACM, but annealing will be above A1 temperature. Then spheroidization, where you are going to do recrystallization annealing or stress relieving, where you are going to do, okay, all those temperatures are marked here. So, now what are the these are the holding temperatures for different heat treatments. And what will be the cooling rate for different heat treatments? Okay, you can see that I can have furnace cooling, so very slow cooling rate. Okay, this will give you furnace cooling, okay, which is what we do in annealing. This is a faster cooling rate, that means I have taken the product out of the furnace and I am doing air cooling. So, furnace cooling means I take the furnace to that temperature, keep it at that temperature for some time, so that my whole product is homogeneously heated to that temperature, and then I switch off the furnace. Okay. So, now furnace is going to cool, my product is going to cool. So, it is a very slow cooling process, okay, and that is what we will have in furnace cooling, okay, and that is what we follow in annealing process. Then I can take the product out from the furnace. So, in air it will get cool, so through convection currents, and then of course, it will be higher cooling rate than furnace cooling, okay, and that is what we do in normalizing. You can do oil quenching, you take it out, put it in the oil, okay. Of course, now oil quenching will be much faster than air cooling, okay. So, you can have faster cooling, and these all cooling curves are superimposed on a CCT curve as shown here, you can see that. So, now you can also understand that if you are doing furnace cooling, what microstructure you will get, if you are doing air cooling, what microstructure I am going to get, if I am doing oil quenching, what microstructure I am going to get, and if I am doing a water quenching, which type of microstructure I am going to get. For example, if you take oil quenching here, my cooling curve has crossed the perlite start temperature, okay, but it has not crossed the perlite end temperature or end curve, okay. So, the transformation is not completed here, and now it is crossing the MS temperature. So, what it will happen in this case, that some austenite will transform into perlite, okay, and the remaining austenite will transform into martensite, okay. So, it will not be a complete transformation into one phase, some portion will be martensitically transformed, some portion will be transformed into perlite, and like that. For air cooling and furnace cooling, you can see that it has crossed the start temperature and end temperature. So, in this case the transformation is complete here, whereas in this case it is not. Or I can do water quenching also. In that case, I will be skipping this nose, so there is no diffusional transformation, and the cooling is fast enough to directly go to the martensitic temperature, where martensite start is there. So, now in this case I will get the martensite directly, okay. So, now we will come to individually one by one and try to discuss each heat treatment. First one is annealing, either you can say full annealing or you can just say annealing. What is the treatment procedure? Heating temperature is about 50 degrees Celsius above A3 temperature. So, A3 temperature is there, so you just go 50 degrees Celsius above that, okay, and there you hold it. So, if you want to have For hypoeutectoid steel it is 50 degree Celsius above A3, and for hypereutectoid it is 50 degree Celsius above A1 temperature. So, in this case we are not crossing the ACM temperature. Okay. And then cooling will be done by furnace cooling. What is the expected microstructure and properties? You will get coarse microstructure, okay, because I am doing very slow cooling here, and of course because I am getting coarse microstructure, this you will understand when we will discuss mechanical properties, that it will have, it is going to have low strength and it will have higher ductility. Note is there, for hypereutectoid steel the heating is done below ACM temperature. This is done to avoid formation of continuous network of proeutectoid cementite on prior austenite grain boundaries. If you remember, when we were showing you proeutectoid ferrite, okay, the proeutectoid ferrite was forming on the grain boundaries, the austenite grain boundaries, okay, and because of that it was getting a continuous network of cementite. Now, please understand that cementite is a hard phase and a brittle phase. So, if any crack in nucleates, it is easy to go along this boundary, okay, and your material will fail without any warning actually. So, this presence of network of cementite provide easy path for crack propagation. So, now we have not discussed about this all the crack propagation and what do we mean by that, but right now you take it from us that from me that this type of microstructure is not good for mechanical properties. Okay. So, I do not want a continuous network of cementite forming, that is why for annealing I am going to do at a temperature A1 at a temperature above A1, not ACM. Okay. Normalizing, heating temperature above A3 as we discussed for hypoeutectoid and above ACM for hypereutectoid. So, in this case I am going above A1. Okay. Why I will be able to do that? Because I am doing a air cooling. Okay. So, in this case your chances of getting those continuous network of cementite is not there. Expected microstructure properties, fine microstructure compared to annealed one, okay, because we are doing faster cooling, more strength because of that and lower ductility than annealed steel. In hypereutectoid steel, normalizing done above ACM, due to faster cooling, cementite does not form a continuous film along the grain boundaries. Okay. So, here I can go above ACM. Then when you have this cementite in this network form, or when you have cementite in perlite also, when you have cementite in this elongated lamellar form, okay, this is not a very good microstructure. Okay. So, for that to take care of this long cementite layers, okay, what we do is what we call as spheroidization annealing. That means I want to make cementite instead of this long lamellas, I want to make it as spherical cementite, okay, and that is why it is called spheroidization. So, heating temperature, again what will be the heating temperature? It will be below A1, okay, to transform lamellar cementite into globular cementite. So, you will have globules of cementite. Cooling, not specific, as no phase transformation is occurring. Okay. In this case cooling is not important because we are not crossing the austenite boundary here. Okay. If you remember, I will just show you very quickly. This was the spheroidization temperature, we did not cross the A1 temperature. So, there is no phase transformation which has started. So, cooling rates are important only when you are having any phase transformation. Okay. In this case, because we have not crossed the austenite, we are just doing annealing at a temperature below A1. So, cooling is not very important here. Okay. So, in this case no specific cooling rate, you can have faster, you can have slower. Okay. Of course, if your product is big, I cannot have fast cooling, otherwise there will be thermal stresses in the material. So, cooling can be decided depending upon the size of the product. What are the expected microstructure? You will have globular cementite, that is why we are doing this annealing. in ferrite matrix expected to increase both strength and ductility. So, you will instead of those long cementite, okay, you will get spherical cementite like this. Why you get this spherical shapes? Long time heating leads cementite plates to form cementite spheroids. The driving force is the reduction in interfacial energy. Okay. So, for the same volume of let us say per cementite, if I have this kind of elongated morphology, you will see that the surface area is maximum is going to be large here, and for a given volume the smallest surface area is always going to be there for a spherical shape. This already we know from geometry that for any given volume, if you have a spherical shape, that is going to have the minimum surface area. Okay, that is why we do this spheroidization. You can have another operation called stress relief annealing. Okay, again some of these ideas are you will be able to understand more clearly when we will go to mechanical properties. When you do any deformation, plastic deformation, you introduce stresses in the material. Okay, and in some cases these stresses are not good for service application. Okay, so we have to do a relieving of stress relieving operation. Okay, and to do that, so to relieve stresses developed during cold working, okay, during any forming or any let us say rolling operation or extrusion operation. So, you any cold working, machining or welding processes, okay, you whatever stresses you are going to develop, okay, that can be relieved by doing a stress relief annealing. So, it is done below recrystallization temperature at around 550 degrees Celsius for plain carbon steel. Recovery is the dominant mechanism during this process. So, this recovery also we will see when we will discuss mechanical properties. Cooling again not specific because we are not doing any phase transformation, although it should be slow enough not to introduce any thermal stresses. As you can see in welding also the stresses are developed because you have thermal stresses, you go to very high temperature where the welding is taking place. Okay, so, you develop thermal stresses in the material. So, when we are cooling it, we should not introduce again the same thermal stresses. There will not be any significant change in microstructure, stresses will be relieved and properties will be restored as observed before a particular operation. So, whatever properties were there before any of these operation, cold working, machining or welding, that will be restored by doing this stress relieving. Okay. Then there is another process called recrystallization, again you will be able to understand more clearly when we go to mechanical properties. Okay. So, after cold working to restore strain hardening capacity of the material and to get fine grain microstructure, this recrystallization treatment is given. Heating temperature is below A1, okay, around 625 to 675 degrees Celsius for plain carbon steel. Expected microstructure, fine recrystallized microstructure, good strength and ductility because of grain refinement. So, all these things we will see when we will discuss mechanical properties, that why we get very good ductility when we good strength when we have grain refinement. This particular term also you will understand when we will discuss the mechanical property, strain hardening capacity of the material and to get fine grain microstructure. Okay. So, this is another type of heat treatment given to materials. Then there is another heat treatment procedure called hardening, okay, and this is to impart high hardness to steel by producing martensite in steel. So, martensite is a very hard phase, okay, very hard, very high strength, very hard. Okay. So, if I want to have hardness or in the material, I will do a heat treatment, give you a heat treatment called hardening. So, this is a microstructure of a martensite. Okay, you can see all these martensite plates are there. Okay, these martensite plates are there in zigzag arrangement. So, heating temperature is about 50 degrees Celsius above A3 for hypoeutectoid and 50 degrees Celsius above A1 for hypereutectoid. Cooling is water quenching or cooling rate high enough to miss the nose of the CCD curve. Okay, so cooling has to be high enough so that I do not have cross the nose of the CCD curve. When you do water quenching, if your product is big, you can understand that there will be lot of thermal stresses in the material. Okay. So, it is always advisable to add alloying elements if you want to do hardening, so that the nose of the curve shifts toward the right and you get enough time to or you can have a slower cooling rate also to get martensite. Okay. Basically, this was not explicitly told to you when we were discussing TTT curve. Okay. So, let me just explain this idea to you, that suppose this is your, let us say we are discussing TTT curve here, okay, and this is my martensite start temperature. So, usually for plain carbon steel, this knows the time which is required to miss the nose is around it is in few seconds basically. So, I have to have very high cooling rate so that I miss this nose. Okay. Now, when you have very high cooling rate, you are bound to introduce lot of thermal stresses. Okay. Now, this also we have understood now that all this kinetics is because of diffusion process, austenite transform into perlite, austenite transform into ferrite and so on. Okay. So, if by any means I can reduce the diffusion process, okay, or if I can make the diffusion slow process, I can shift the nose towards the right. Okay. So, by adding alloying element, okay, let me plot a new TT curve in a different color. Suppose I add alloying element. So, now when you have transformation from austenite to any other phase, there has to be redistribution of this alloying element. In austenite they may have different solubility, in ferrite they may have different solubility. So, they have to, this alloying element also have to redistribute between austenite and ferrite. Okay. So, what will happen because of that? When I add alloying element, this curve shifts towards the right. So, it will go somewhere like this. Okay. So, now I am going to give enough time for having a martensitic transformation. So, now I can have much slower cooling and still I will be able to get martensite, because I am able to skip the nose. By doing that, I am reducing the thermal stresses. Okay. So, that is the idea of adding alloying elements in steel. If you have plain carbon steel, you have to have only water quenching to get martensite. Okay. So, that is what we are saying, water quenching or cooling rate high enough to miss nose of the CCT curve. I can shift the nose of the CCT curve by adding alloying elements, okay, and let us say then I can do a martensitic transformation by oil quenching also, which is a much less severe process. Okay. Now, since martensite is a very hard and brittle phase, okay, we have not come across this term still now, okay, but take it from me that martensite is a very hard and brittle phase. Okay. So, what happens is that if you have a martensitic steel, okay, in a plain carbon steel, suppose you have martensitic phase, you cannot use it in the any application, because if you have any small impact also it will fracture. So, to impart any ductility to steel after hardening, okay, what we do is we do a heating at around 400 to 500 degrees Celsius, so that carbon precipitate out. So, when you go, as I told you, if you remember, martensite is a metastable phase. Okay. So, if I take it to a little bit again higher temperature, what will happen is it will dissociate into two stable phases, which is ferrite and cementite. So, if I do a little bit heating, what will happen, the carbon which is trapped in the martensite during diffusionless transformation, okay, that will be able to come out in form of cementite. Okay. So, that is what is we are saying here. The expected microstructure is martensite with precipitates of carbon, improves ductility, however at the cost of strength. The strength of this martensite, the tempered martensite, will be lower than the hardened martensite, okay, and but it will have better ductility. Some notes are there. A sample with martensitic microstructure is hard but brittle. During tempering, martensite decomposes to ferrite and cementite on heating. Decomposes to ferrite and cementite. On heating. Tool steel has a quench hardness of around 65. So, this we will see what do we mean by these hardness values, which is tempered to get a hardness of around RC 45 or 55. Okay. Tool steels are the steels where you do some alloying in the steel, okay, and these can be easily hardened by oil quenching, okay, and that is what you use in industry for making dies and so on. Then there are a couple of very interesting processes. One is, for example, Mar tempering. It is to reduce the thermal stresses in hardened steel. So, you can have water quenching also, okay, but to reduce thermal stresses we can do a little bit, we can be smart enough here. We can use a trick here, and that is what we do in Mar tempering, that to reduce the thermal stresses I use a process called Mar tempering. I will show what do we mean by that. So, heating temperature is about 50 degrees Celsius above A3 for hypoeutectoid and 50 degrees Celsius above A1 for hypereutectoid. Cooling stops just before the MS temperature. Okay, so, you can have very high cooling rate, but you stop at a certain temperature above MS temperature for achieving uniform temperature throughout the sample, and then it is quenched. Expected microstructure properties, martensite with lower stresses will be formed. Okay. Sometime when you do this kind of very fast cooling, what happens is martensite itself is hard and brittle, and at the top of that you also have these thermal stresses which can introduce some cracks in the material even before any stresses are applied. Okay. So, that we do not want. So, we can reduce the thermal stresses by doing a Mar tempering operation. There is another very interesting heat treatment called Aus tempering. Okay. What we do in this is to get bainite by isothermal transformation. Now, if you remember, I said that you cannot get bainite, okay, in normal coolings if you are doing continuous cooling. So, bainite can be, of course, you can get by isothermal transformation. So, heating temperature is again same as we did in Mar tempering, cooling more than critical cooling and then isothermal transformation in bainite region. Expected microstructure bainite, good strength and ductility. So, this is what these two treatments are called. So, Mar tempering you do very fast quenching, okay, just avoiding the nose where the diffusional transformation can take place, okay, and then we are holding just above the martensitic start temperature to have equalized temperature throughout the sample. So, this will by this we are trying to reduce the thermal stresses in the material. Okay, we are giving enough time for temperature to stabilize and have uniform temperature throughout the product, and then you are doing the quenching, okay, to get the martensite. Similarly, I can do for Aus tempering that I skip the nose, have cooling up to this point, and then I am holding isothermal holding to get bainite. So, this is what we call as Aus tempering. Okay, and you can see that just skipping the nose. Okay, so there I can define a cooling rate which is just skipping the nose as critical cooling rate. So, if any cooling rate which is more than this is bound to skip the nose here. So, this is a cooling rate which is critical cooling rate which is just missing the nose. So, when you have a certain TTT diagram, okay, if I say the cooling rate should be more than the critical cooling rate, that means it is more than a cooling rate which is just skipping the nose. Okay. just to be safe that there should not be any diffusional transformation during the cooling. Okay. So, this is Marr tempering is a very smart process. You can see that I am holding it to avoid the thermal stresses. Okay. So, these are the different heat treatments. There are in fact even more heat treatments possible with materials. Okay. One has to be smart enough to devise those heat treatment. Okay. And these basic ideas only give you new ways to devise these new heat treatments. Okay. And it will not be an end of heat treatment research. People will keep coming with new heat treatment depending upon their understanding of the microstructure, the kinetics, the thermodynamics and so on. Okay. So, with that, thank you.